Welcome to mathematics class, and now we are going to talk about areas of parallelograms and triangles. So let us see the topics to be covered. First, we will have a brief introduction, and then we will talk about figures on the same base and between the same parallels. After that, we will look at parallelograms on the same base and between the same parallels, and finally triangles on the same base and between the same parallels. So let us start off with the introduction. Now we all know that two congruent figures have equal areas, right? Like here it is shown triangle ABC and triangle DEF have equal areas, right? Because they can overlap onto each other. But the converse is not always true, right? The converse is not always true. Why? Because if two figures have the same areas, not necessarily all the two figures will be congruent, right? If the areas of two figures are the same, not necessarily they have to be same with each other. They have to be alike. Let us see one example. Areas of rectangle with side 9 cm and 4 cm is 9 into 4, which is 36 cm square. You can see here 9 into 4, 36 cm square, right? The area of this rectangle. Now if we find out the area of a square with side 6 cm, we actually get the area same 36 centimeters, right? 6 into 6, 36 centimeters. So you have seen that if the areas are same, not necessarily both the figures have to be same. But if the two figures are congruent to each other, or the two figures are exactly alike, then obviously both of their areas must be the same. And one more thing which we must know: if a planar region is formed by two or more non-overlapping planar regions, then the area of the bigger planar region is the sum of the individual smaller planar regions. Like here, a bigger planar region, which is the bigger square, is actually divided into smaller figures 1, 2, 3 and 4, right? It is divided into 4 quadrilaterals. Now the area of this big figure is actually the sum of the individual portions, right? And we will use this characteristics, like if the areas are same, both of the figures need not be the same, and the sum of the individual parts of a whole figure actually give us the area of the whole figure. Now we will use these two concepts in the following slides. So let us jump to our next topic: figures on the same base and between the same parallels. So here you can see we have drawn two parallel lines. So let us draw one closed figure. I have drawn a quadrilateral, which is obviously a trapezium. Two sides are parallel, AB and DC, right? So we have drawn a quadrilateral between two parallel lines, or we can say between two parallels. Now let us consider one more quadrilateral. Let us consider MNCD, the blue one. Let us consider the blue quadrilateral. You can see this blue figure is actually on the same base, right? The blue figure is on the same base DC, and also the blue and the red figures, both of them lie between the same parallel lines or between the same parallels, right? Both of these figures lie between the same parallels. So these kind of figures are said to be on the same base and between the same parallels, right? Such figures where both of them have a common base and both of them have the same height or they are between the same parallels are called figures on the same base and between the same parallels, right? And of course the heights are same because for lines which are parallel, their shortest gap, their perpendicular gap between these two parallel lines is always constant, right? Or the height between these two lines is always constant. So the height for these figures are also constant. And here are some examples where figures have the same base but they don't lie on the same parallels. Like for the first figure, if we draw a parallel line which is passing through AB, you can see EF is not lying on that parallel line. Similarly, for these two figures, these two parallelograms PQRS and MNRS, for these two triangles you can see they have the same base BC, but if we draw a line parallel to BC through A, you can see D is not lying on that parallel line. Similar case with AB, the quadrilateral ABCD and the triangle PCD. If we draw a line passing through AB which is parallel to CD, you will see P is not lying on the parallel line, right? So such figures do not lie on the same parallel lines even though they have the same base. Now there are also figures which do not have the same base but may have the same height, or they might lie between the same parallels. You can see the triangle ABC and triangle BDE. These two triangles have different bases BC and BE, but both of them lie between the same parallel lines, or they have the same height, right? So you can see what we actually mean by figures on the same base and between the same parallels. At least one of their bases, like either the top one or the bottom one, the top side or the bottom side must be same for both of them, or they must have a common base and they must lie between the same parallel lines. So here is one question: which of the following figures lie on the same base and between the same parallel lines? Let us take figure by figure, right? Let us take the first figure. So you can see we can see that if we take the base CD and then we find two figures which are on this base, which is this triangle PCD and the quadrilateral ABCD, these two figures are lying on the same base and the two sides AB and CD, we are assuming they are parallels, so we can tell that these are the figures on the same base and between the same parallels. Same base is CD and the same parallels are AB and CD. So here we have considered the triangle PCD and the quadrilateral ABCD. Let's consider the second one. We can see two figures, right? The parallelogram PQRS and a small trapezium MNRS. Now you can see, even if we draw a parallel line passing through PQ, MN would not lie on it, or though they have the same base, they do not lie on the same parallel lines. So this figure does not lie on the same base and between the same parallels, right? Only one of the criteria is fulfilled, not both. Let's talk about the third figure. Now you can see, if we look by taking the figure sideways, let us take QR as the base. Let us take QR as the base. You can see we have a triangle and a parallelogram once again. QR is parallel to PS, right? QR is parallel to PS. So the triangle TQR and the parallelogram PQRS lie on the same base, which is QR, and between the same parallels, which is QR parallel to PS, right? So this is the case where figures lie on the same base and between the same parallels. Let us take the fourth one. Now, even if you see from any angles, they don't have a common base, right? The least we can find is this side, where we have the base of this triangle PQ and the base of the parallelogram as BC. So you can see we don't have a common base, and even if you look at it from any angle, any side, you will not find a common base, or they are lying between the same parallels and they are fulfilling both the criteria. So these are not figures on the same base and between the same parallels. Let us consider the next one, fifth one. Now we can see two trapeziums, a smaller one and a bigger one. Smaller one is APCD, right? And the bigger one ABQD, right? We can see two figures. So if we consider any one as the base, let us consider AD as the base. If we consider AD as the base and AD is parallel to BQ, if we consider like this, then you can see both the trapeziums have a common base, which is AD, and both of them lie between the same parallels, right? They lie between parallel lines AD and BQ. So this is a figure on the same base and between the same parallels. And for the sixth one also you can try, but you will not find a common base. So this is also a case where figures are not on the same base but between the same parallels. So you can see how easily we can classify figures based on their common base and lying between the same parallel lines. Now once we have identified how we can classify these kind of figures, let us see some special figures and find out some of their characteristics. Let us look at the quadrilateral parallelogram. Parallelograms on the same base and between the same parallels, right? Now you know how will they look like, right? They will be on the same base and they will lie on the same parallels. They will lie between the same parallel lines, right? Now to find out their characteristics, let's do a quick experiment. We have a parallelogram, right? We have a parallelogram on a piece of cardboard. So what we do, we draw MD. M can be any point on the side AB, right? Then what we do, we cut along DM. We cut along DM. You have seen that we have cut along DM and put that side aside, put that part aside, right? This part has been put aside. Now what we do, we bring this part this side. We bring this part this side. Now you can see AD was parallel to BC, right? AD was parallel to BC. So we can easily join them. AD was parallel to BC and also AM was parallel to CD, right? From the earlier figures. AM was parallel to CD and AD was parallel to BC. So we can easily join them, right? We can easily join them. So we have joined AD along BC. So you can see we have got one more parallelogram, right? We have got one more parallelogram which is different from the earlier one, right? It is looking a bit slanted. Now let us compare it with the earlier one. The earlier one is shown in gray color and the new one is transparent. So you can see, if we consider the two parallelograms, the old one gray color and the new one, you will see both the figures are on the same base and between the same parallels, right? They are on the same base CD and between the same parallels, which is AM and CD, right? They were parallel lines as it is a parallelogram, and they are on the same base. So these two parallelograms, the older one and the newer one, both of them form the figures on the same base and between the same parallels. But notice one more special thing. We have not altered the area of the parallelogram, right? The area still remained the same because we had just taken this part off and stuck it on the other side, right? So this part and this part must have the same area, right? Because they were the same. We had just taken AMD from one side and placed it on the other side. So both of these areas must be the same, right? So if we look at this central part, let us call this area as X, the area of the central part which is not touched at all, right? And let us call the area of this smaller triangle as Y. So this also must be Y, right? So if we consider the area of the earlier parallelogram, the gray part, it is X plus Y, right? The area of the gray part, area of the earlier parallelogram is X plus Y. Now what is the area of the new parallelogram? What is the area of the new parallelogram, which consists this X part and this part? You will see that the area has still remained the same, right? Because we haven't added any area or taken away any area, right? We have just put one of its part on the other side. So the area must remain the same, and they are the same, right? We have seen just now. So you can see, if we have two parallelograms on the same base and between the same parallel lines, their areas are the same, right? Or the areas of parallelograms on the same base and between the same parallels are equal. And actually, for any two similar figures, if they are between the same parallel lines and on the same base, then their areas are always equal. And we can also show this mathematically by showing that these two areas are actually the same, right? And if we add the area of the central part with any one of these areas, we will actually get the area of the parallelogram, right? If we add the central part with the left hand side part, we will get the area of the older parallelogram. If we add it with the right hand side part, we will get the area of the new parallelogram, right? So let us show that these two areas are the same. Let us consider these two triangles. You will see angle DAE is equal to angle CBE. These two angles are the same. And why? AD is parallel to BC, right? AD is parallel to BC because ABCD are the vertices of a parallelogram. ABCD are the vertices of a parallelogram. So AD parallel to BC, and if we take AB as the transversal or AE dash as the transversal, angle DAE and angle CBE prime are corresponding angles which are equal. So angle AED, which is this angle, and angle BE prime C, which is this angle, are also equal. And why is this? If we consider the parallel sides of quadrilateral EDCE prime, EDCE prime are the vertices of the new parallelogram, so the opposite sides must be parallel, or ED parallel to E prime C, right? So these two are corresponding angles, right? These two are corresponding angles, and therefore they must also be the same. So we have got this angle equal to this angle, and the new angle equal to this angle. So we have got two angle equality. And you can also see AD must also be equal to BC or BD prime, anything you can call it. AD and BD prime, both of them are same. Why? Opposite sides of a parallelogram are equal, right? So you can easily say triangle ADE is congruent to triangle BCE, or this triangle is congruent to this triangle, right? So both of their areas must be the same, right? Their areas must also be equal. So if their areas are equal, we can add the individual parts with the central part and show that the summation is always equal, or the areas of both the parallelogram, the old one and the new one, are the same. So let us apply these concepts to solve one question. ABCD is a parallelogram and EFCD is a rectangle, as shown in the figure. Also, AL is perpendicular to DC. AL is perpendicular to DC. Prove that area of ABCD, and this is the notation for areas, area of quadrilateral ABCD is equal to area of EFCD, right? So let us solve part 1 first. We will look at part 2 later. So let us prove these two areas of the quadrilaterals are equal. I hope you can see the quadrilaterals. ABCD is a parallelogram, EFCD is a rectangle. So as the rectangle is also a parallelogram and both of them lie between the same parallels and are on the same base, you can see both of them are on the same base DC, and both of them lie between the same parallels, EB parallel to DC, right? Because EF is the side of a rectangle and AB is the side of a parallelogram, so obviously the opposite side, which is DC, must be parallel to them. So ABCD, the parallelogram, and the rectangle EFCD, both of them lie between the same parallels and both of them lie on the same base. Since they fulfill these two criteria, we can say both of their areas are the same, right? Or you can prove it in a longer way, like we had done earlier. You can prove the area of this triangle is equal to area of this triangle, and again you can add the central part to any one of them and show that the area of this rectangle and the area of this parallelogram are the same. So you can see we have used this theorem or this criteria to solve this question in just one line. So let us solve the second part. We have to show area of parallelogram ABCD is DC into AL. DC into AL. So how will we show that? It is very easy. Area of ABCD is DC into FC. Why? because the area is the same as that of the rectangle, right? Area of the parallelogram ABCD is the same as the area of the rectangle. And what is the area of the rectangle? The multiplication of two sides. So one of the sides is DC for the rectangle and FC, right? So DC into FC gives us the area of the rectangle, and the area of the rectangle is equal to the area of the parallelogram. So area of the parallelogram ABCD is DC into FC, right? Now AL is perpendicular to DC, right? AL is perpendicular to DC. So this AFCL is also a rectangle, right? AFCL is also a rectangle. Or if we can consider the length of FC, we can also consider the length of AL, right? Because both of them are same. AFCL is forming one more rectangle. Their opposite sides must be the same. So you can say AL must be equal to FC. So let us put these values in our equation, right? And we can easily see that if we replace FC with AL, which is of the same length, we can easily get area of parallelogram ABCD equals DC into AL. So we have proved the given question, whatever was given, by using the simple concept that areas of parallelogram on the same base and between the same parallels are always equal. And also you can get one more information from this, that if anyone asks you to find the area of a parallelogram given their base and the height of the parallel sides, if these two parameters are given, you can easily find the areas, right? The area of any parallelogram is base into the altitude, or the distance between the two parallel sides, of which one of the sides must be the base, right? Base times the altitude is the area of any parallelogram. So this is an extra information which you can get from this question. So let us move on to the next topic, triangles on the same base and between the same parallels. Triangles on the same base and between the same parallels also have equal areas. You can see, if we consider AP parallel to BC and the two triangles ABC and PBC, if we consider these two parallel lines and the common base BC, we can tell ABC and PBC have the same areas. And you can easily show this. You can easily explain this using area of a triangle is half into base into height. Now the base is same for both of them, right? The base is same for both of them. But if we consider the height, the heights are from A to BC and from P to BC, right? And for two parallel lines, the height is always constant. So here we also get the height as the same. Base is same, height is same. So easily we can say half into base into height is the same for both of them, or the area is the same for both the triangles lying on the same base and between the same parallel lines, right? And if you consider the converse statement, which is two triangles having the same base or equal bases and equal areas lie between the same parallels, or if you are given that two triangles have the same base and the same areas, you can easily prove that the other side, the other line which is given, is parallel to the base. And you can also prove this using different angle theorems of two parallel lines and using a transversal. So let us use the concepts in a question. Show that a median of a triangle divides it into two triangles of equal areas. Here it is given triangle ABC and AD is the median, or D is the midpoint of the side BC. D is the midpoint of the side BC, or you can say BD is equal to DC, right? This is the information given to us. And now to make this question easy, what we do, we draw a perpendicular line which is perpendicular to the base BC. We draw AN perpendicular to BC. AN is perpendicular to BC. So for triangle ABD, which is 1/2 on the side of the median, the area of that part is half into BD, which is the base, into the height, which is AN. Half into base into the height AN, right? So this is the area for triangle ABD. Now the area of triangle ADC. Triangle ADC, if we consider, it is half into base DC into height AN. Half into height into base. So we have found the area of triangle ADC also. Now are these two areas the same? If you compare the bases, because for both of them heights are the same, right? AN, both of them heights are the same, so we must find out whether their bases are same or not. If their bases are same, their areas must also be the same. And we find here, as D is the midpoint of side BC, then obviously BD will be equal to DC, right? BD is equal to DC, or their bases are equal. So if you replace any one of them, you can easily get the area of the other one. So half into BD into AN is equal to DC, half into DC into AN, because BD is equal to DC and the rest of the terms are the same. So you can easily say area of triangle ABD is equal to area of triangle ADC, or the median has actually divided the triangles into two equal parts having equal areas, right? And you can take this question or the statement of the question as a theorem that a median of a triangle always divides a triangle into two parts of equal areas, right? And you can use this theorem in many questions, and of course while using this you must state the theorem as well. So let us do one more question. ABCD is a quadrilateral. You can see ABCD is a quadrilateral, and BE is parallel to AC. BE is given, which is parallel to AC, and also BE meets DC produced at E. When DC is extended to E, BE meets DC at that point, right? Or you can say DCE is a straight line, right? DCE is given as a straight line. AC parallel to BE is given, right? And let us see what else is given. Show that the area of triangle ADE is equal to the area of quadrilateral ABCD. Area of triangle ADE, the bigger triangle ADE, right? This area we have to show that it is equal to the quadrilateral ABCD, right? So you can see the figures actually look very complicated, and we have to show that the area of a quadrilateral is equal to the area of a triangle, right? And the question actually sounds so difficult, but actually if you use the concepts which we have learned so far, the question is very simple. If observed closely, you will find area of triangle ACE, triangle A, the triangle ACE, area of triangle ACE is equal to area of triangle BAC. Both of these have the same area. And why? They have the same base, and that is not the base actually. They have both the same base, which is AC, right? Both of them have the same base, and they are lying between the same parallels, BE parallel to AC, right? If we consider AC as the base and the two parallel lines AC and BE, you will see triangle ACE, which has the base AC, and triangle BAC, which again has the base AC. Both of them have the same areas, right? So we have got one thing. Now let us look at this part which is common to both of these. This part ADC is common to both quadrilateral ABCD and to the triangle ADE, right? So let us use this common part now. Let us add the common part to both these areas, and obviously it will not change the equality, right? If two quantities are equal and on both the sides we add two equal quantities, obviously the equality will still hold, right? So area of triangle ADC, if we let's take the area of the central part as X, and the areas of the two triangles let us take as Y, right? The area of triangle ACE we have taken as Y, and the area of triangle BAC we have taken as Y. So area of triangle ADC plus ACE, or X plus Y, is equal to area of triangle ADC, which is X, plus area of triangle BAC, which is Y, right? So you can see the equality still holds. Now if we consider these areas, if we add these two areas, what figure do we get? On the left hand side, triangle ADC plus triangle ACE, triangle ADC, and triangle ACE. What did we get? We got the triangle ADE, right? On the left hand side, we have the area of triangle ADE splitted into two parts, right? And on the right hand side, triangle ADC plus BAC, right? So what is the figure? Which figure's area is this? It is the area of ABCD, right? When we are joining these two areas, we get the area of the quadrilateral ABCD, right? So area of quadrilateral ABCD here is splitted into two parts once again. So you can see easily that both of these areas are the same, right? We have proved that the area of triangle ADE is actually the same as the area of triangle ABC, of area of quadrilateral ABCD, right? So let us revise what we have done. We see that we have two parallel sides, AC and BE, and we also see that we have two triangles with a common base, AC. And what are the two triangles? Triangle ACE and triangle BAC. Now why did we consider these triangles only? You can see, if we see the questions, if we see the question given, we have to show area of triangle ADE equal to area of quadrilateral ABCD. For both of them, the common part is triangle ADC, and if we take the rest of the parts, we are left with two triangles which are ACE and BAC. We are left with these two triangles. If we keep aside the common triangle, these two triangles have the same base and they lie between the same parallel sides. And by using the theorems or the statements which we have learnt so far, we can say that the area of these two triangles is obviously the same, right? And now if we add the areas of these triangles individually to the common triangle, we get the areas of the entire figures ADE and ABCD, and we can say that the areas of these two figures are the same. So you can see how we have easily used the theorems and the statements we have learned so far, which is triangles or parallelograms on the same base and between the same parallels have the equal areas. So in this class we have learnt how to classify figures on the same base and between the same parallels, and also we have learnt about parallelograms and the triangles which have the same base and lie between the same parallels and they have the same areas, right? And we have also learnt how to use them to solve different questions. Thank you and see you again.